So once again, this is going to be a webinar on the Topology Toolkit. And I have to actually make a disclaimer. I don't know topology myself, so I'm not a topologist by training. I'm a computational astrophysicist. And so everything I'm going to show you today, I learned in the past few weeks. So I decided to take a detailed look at the TTK, the Topology Toolkit. And everything I'm going to show you today is just based on a very steep learning curve from the past few weeks. So I'm going to approach this not as a topologist, but as a research scientist. So the idea is that I have some data set and I want to analyze it using topological analysis. So if you have a multidimensional scalar data set and you want to apply topological analysis for it, you really want to look for some measurable topological attributes, right? So things that immediately come to mind when you say the word topology is things like measurement of connectedness. So if you pick an object or a domain and then pick any 2 points inside this object, then you can find, you can look for an inside path to connect these 2 points, right? So if you can find an inside path, then it's a single component. Or you can be looking for, you can be counting non-contractible cycles. So you can pick up a closed loop inside your object or your domain that you can or cannot squeeze down 2 points. So everybody knows that topological, let's say a mach is similar to a donut, right? So a mach with a single handle is similar to a donut, but is distinct from, let's say, a sphere, right? And there are many other measurements of topological attributes. So, and then you apply these to your data set. And I can give you many examples. So some of them are listed in this slide. For example, you're doing, let's say, molecular analysis. And actually, let's say you're running something like Gaussian or some other quantum computation package. And then you're solving Schrödinger's equation. And then the output is a 3-dimensional electronic probability density distribution, right? So it's a spatial field in 3D. And then based on this field, there's nothing else. You want to visualize, let's say, atomic bonds or atoms, etc. And so one way to do this will be to apply topological analysis to it. So basically subdivide your domain into segments, find the critical points, critical lines, et cetera, and this will correspond to atoms, atomic bonds, and other elements. Perhaps you're doing material analysis. So you're doing, let's say, porosity measurement, or you are looking for cavity deformation, defect identification in your solid body, et cetera. So TTK is really a perfect tool for doing this kind of analysis. Perhaps you're doing neural pathways, well, analyzing neural pathways. So that's called connectonomics. Very popular application of TTK is CFD, computational fluid dynamics. So typically you would have a turbulent flow, and then you'll be looking at, let's say, vorticity regions or turbulent regions, or perhaps bubble formation rates, et cetera. And there are many other applications. So separate at the bottom of this list, I have image segmentation. So this is a very popular application of topological analysis, and I'm going to talk about image segmentation towards the end of this talk. So in all these cases, you are interested in some phenomenon in your multidimensional scalar field in the data set. And the trick really is to derive its measurable topological equivalent. So sometimes that can be easy, sometimes that could be really hard. So, but in all cases, it's really good to know the underlying tools. So the goal of this webinar is really to show you not so much to teach you topology, but to show you TTK and to walk you through several main workflows with TTK. So before we go to TTK, there are actually a few definitions that I need to introduce, because without these definitions, you'll be completely lost. So let's take a look at a one-dimensional scalar function. And we're going to be defining persistent intervals. So imagine a function that looks like this, and then we are going to sweeping this function in the function value, so the vertical axis, from -infinity to +infinity. So imagine a horizontal line that goes from -infinity to +infinity, so it rises, right? And this horizontal line intersects the function, and then we get disconnected components, right? So once we reach we're starting from -infinity, we go up, and then we reach the first local minimum, we get the first component, and then we keep going, then we reach the second local minimum, we get the second component, then we reach the third minimum, we get a third component, right? So now we have 3 components, 3 disconnected components, or yeah, 3 disconnected components. And then as we keep going up, when we reach this local maximum, these 2 components on the right merge into a single component, right? So what you can do is you can actually pair threshold or critical points that create components with those that destroy these components, right? So there is one component right here in the middle that is being born at this local minimum. And then this component merges with the rightmost component at this local maximum, right? So this component only exists for these function intervals. So this is called a persistence interval or persistence value of this component, right? And as you keep swiping up, you can continue pairing the critical points that create components and critical points that destroy these components. And for this particular function, this is what you get. So you'll have three components, and these are the persistent intervals or persistence values, right? And so in 1D, the critical points are local minima and maxima, right? So there are only two types of critical points in 1D. And you can plot all these persistence intervals on what is called a persistence diagram. So the idea here, you can see the persistence diagram on the right. The idea is that on the horizontal axis, you plot the function value at a component's birth. And then on the vertical axis, you plot 2 points. So the first point corresponds to component's birth, and the second point corresponds to component's disappearance, right? So basically, the length of the vertical interval here, starting from the diagonal, and the length of the vertical interval is going to give you the size of the component. So all small features, small components, noise, they're going to be very small. They will produce very small persistent intervals, and all these persistent intervals are going to be clustered very close to the main diagonal. Right. So then you can perform domain segmentation. So you can divide your region into your domain into monotone regions between the critical points. So these regions will be simply be defined based on the gradient sign. And then you can define mountains, right? So a monotone, so here, let's say we have a monotone region right here, it's increasing. Then we have a monotone region that is decreasing. And actually, let me define my mouse pointer. It always dies on me. So I can actually see it better. So here we go. So here we have a monotone region that is increasing, a monotone region that is decreasing, and these are centered around the maximum, right? So here we have a mountain, a couple of monotone regions forming a mountain. Here we have a basin, a couple of monotone regions around the minimum, and so on. So here is another basin, here is another basin, and so on, right? So this is in 1D. Then you can also define a join or split tree of connected components. So if we look at the function from the previous slide, then here we're going to, as we're sweeping in function value from -infinity to infinity, we can find a join tree of connected components, right? So we have these connected, these connected or disconnected intervals, and these intervals or components merge into a tree, right? And eventually you have a single, just a single component, right, at the top of the tree. So here we have a join or a merge tree. If we split this function, if we rotate this function 180 degrees upside down, then we get, instead of a join tree, we get a split tree of connected components. So we get a tree that splits into leaves, and then the leaves correspond to the maxima, right? So the regions adjacent to the leaves are the regions, the mountains or regions adjacent to the maxima. And so in TDK, you can easily do this kind of analysis on 1D, 2D, multidimensional function. So TDK lets you compute persistence diagrams. So what you saw in the previous slide, right? The persistence diagram, so a diagonal and then a bunch of components. And then a persistent curve. So a persistent curve is basically a distribution of these persistent intervals. So typically you have a lot of noise, so lots of small intervals, and then a few main features, so a few major intervals. Then you can, in TDK, you can apply a filter to build a tree, let's say a join tree or a split tree, and then you can identify the regions attached to the leaves. Let's say in this case on the right, we have the maxima attached to the leaves, and these can be identified by simply specifying the region time in the output of the TDK filter. You can perform topological segmentation, so you will be dividing domain into monotone regions based on the gradient sign, and you can perform topological simplification as well. So here the idea is that you delete small components, components that have very small persistence values or persistence intervals, and only leave the big ones. So in TDK, there are multiple filters to do all these kind of things on the multidimensional data. Yeah, the pointer looks worse for me. Okay, I'm gonna switch off the pointer then. Yeah, unfortunately there is a delay in Zoom, so, and I cannot control this. So now thank you. Let's imagine a two-dimensional scalar function. So here I have a function with, it's 2D function with 3 Gaussian peaks. So I sweep in function value from -infinity to infinity. And the colorless regions show the subdomain with function value lower than the sweep value. So now we have, here we start with a single component, and then the single component splits into multiple components. Actually, this hole splits into multiple holes at the saddle points, right? So in 2D now you have 3 types of critical points. You have minima, maxima, and then saddle points. And saddle points are simply points where the coordinates derivatives are all 0, but these points are neither minima or maxima, right? So for example, here is a saddle point where we have where the hole is splitting into 2. Here we have another saddle point, and these are the maxima. So the maxima where the holes disappear. And so similar to 1D, in 2D, you can also perform domain segmentation. You can break your domain into monotone regions based on the gradient sign. And of course, these are going to be bound by the integral lines. So the integral lines are orthogonal to the contours. And so in 2D, you have the same definition for mountains and basins, but there are also ridge lines and valley lines. Like, so a ridge line is a line where you have a descent on both sides of the line, and then a valley line is a region where you have on both sides of this line, you have a positive gradient. All right, so in 3D, of course, the topology becomes much more complex. In 3D, and by 3D, I mean a 3-dimensional scalar function, you have minima, maxima, and also 2 kinds of saddle points. So 1 saddles are located between the 2 minima and 2 saddles are located between 2 maxima. So here's a diagram that is floating around the web. I saw it in many different TDK presentations, so I'm not sure who created it first. So the idea is, let's say you're at a minimum, and then while you're sitting at a minimum, and you look in all directions. So no matter which direction you go, starting from the minimum, your function will always be increasing, right? Because you were at a local minimum. If you were at a local maximum, no matter which direction you go, so there are 2 angles, there is a sphere, right? So in any direction you go in 3D, your function value is going to be disappearing. So a saddle is a critical point, one saddle is a critical point where you have 2 regions of decreasing gradient, and then in between you have increasing gradient. And then on the other hand, you can have a 2 saddle. So similar to 1D and 2D, monotone regions can be combined into mountains and basins. There are also ridge lines and valley lines like in 2D, but there are also saddle connector lines, ridge surfaces separating the mountains, and valley surfaces separating the basins. So visualizing this in 3D, of course, is more difficult, so I don't attempt to draw this. And so TTK lets you do this kind of analysis fairly easily. So TTK stands for the Topology Toolkit, and it's a standalone package that is open source. So development started in 2014, first public release in 2017. And the lead author, Julien Carny, is from Université Sorbonne, but there's also a very active development community. And I want to say that the documentation is really excellent. So there are, if you go to TTK website, you'll find tons of tutorials, walkthrough videos, et cetera, et cetera, et cetera. This is one of the best documentation out there for any open source package. So really excellent. And they're also each year at IEEE's conference. So it's a yearly visualization conference. They have really good half-day tutorials on TTK, and a lot of materials that I'm going to present today are actually borrowed from these tutorials. So TTK by itself is a C++ package, but it can also be, so you can run it as a standalone C++ code, and it has also some visualization component, but it can also integrate into VTK. So if you use TTK with C++ and VTK, so VTK stands for Visualization Toolkit Library, which is a very common library for multidimensional computer graphics, then your code is going to be roughly 3 times shorter than pure C++ code. And also there's also a Paraview Python code, which produces even more compact code, right? So you don't have to use TTK from pure C++, which is great. And also there's a Paraview plugin. So today I'm going to be concentrating only on the Paraview plugin. So all workflows I'm going to show you will be inside Paraview. So how do you install TTK? Well, in their documentation, there are detailed instructions for compiling TTK on Mac, Windows, and Linux. The instructions are very detailed. Unfortunately, in practice, things are more complex than they appear from the documentation. So I compiled TTK natively on my MacBook, And I actually had to spend 3 full days trying to do this. There were lots and lots of problems. So the thing about compiling TTK as a plugin for Paraview is that you cannot just take off-the-shelf Paraview and compile a plugin into it. So you need to take a specific version of Paraview, and then you have to apply a TTK patch to this. You have to apply a TTK patch to Paraview. And unfortunately, the latest available, well, officially stable TTK patch for Paraview is available only for Paraview 5.6. So the latest stable Paraview is 5.8, and there's also 5.9 release candidate available now. So basically, that means that if you want to use TTK in Paraview, you have to use a much older version of Paraview, so which is about a year and a half old. And so when you download Paraview 5.6, basically you compile Paraview 5.6, you compile TTK, and then you follow all the instructions. And when I do this on my MacBook, so it compiles. I start Paraview with TTK, and it just hangs. So it shows 100% CPU activity, spinning wheel, and nothing happens. And I waited for, believe me, I waited for many hours, and nothing happened. So it's not just Paraview being slow. So sometimes you can see this problem when you try to compile Paraview with MPI, and 100% CPU activity for parallel application means that it can be just waiting for incoming message. There's no incoming message, so it's a maybe wrong usage of parallelism or a parallel bug, but not in this case because I specifically disable MPI. So I would compile. Compilation takes on my laptop takes something like 3 hours. I have only 2 cores, and then I would start it, and it would just hang. No error messages, no debugging information, nothing. So I spent a few days trying to trace it down, and eventually it turned out that even though I was installing, trying to use the latest version of Qt, Paraview was picking the older version of Qt on my MacBook. So it was picking the default version of Qt. So I have to specify this variable. Oops, sorry. I have to specify this variable, Qt5, inside Paraview installation. And another problem was so of course I'm using the latest version of Python, which is Python 3.8 on my notebook, and TTK does not work with Python 3.8, so it has to compile for Python 3.7. So I did install Python 3.7. I followed all the instructions on the in the documentation, and they didn't work. So what you have to do, you actually have to specify some other variables in addition to what is provided in documentation. So basically, NumPy has to point to the right version of NumPy from Python 3.7. Python include directory, Python library, and a few other things. So here just list the things that were not mentioned in the documentation. So once you go through all this, it compiles and it runs. So I can actually, so on my laptop today, I'm going to show you tons of workflows. And I have an Alice on my laptop, which is actually pointing to this specific build of Paraview 5.6 with TTK included. So fortunately, if you want to install and run Paraview with TTK on your computer, you don't have to go through this. So I went through all of this, this exercise only because I wanted to know how all this works. But fortunately, you can actually use a Docker image for Paraview, a Paraview server with TTK. So the idea is that you install your Docker desktop, so it works on Linux, Mac, Windows, and then you run a pre-built Docker image. So the Docker image is available from Docker Hub. So you just download it, and then you run it. And what will happen when you run it is that inside this Docker image, you will have a Paraview server waiting for incoming connection. And then from outside the Docker image on the same machine, but not inside the Docker image, just natively, you start the Paraview application. So it's going to be a Paraview client. You connect it to the Paraview server waiting on port 11111 on your computer, and then you have a local Paraview with TTK running. So towards the end of this webinar, I'm going to show you a demo where I actually use a similar approach on a compute canal cluster. So on CEDAR, I'm going to be running TTK from a Singularity image. So anyway, let's just jump to workflows. Are there any questions at this point? All right, so I'm going to show you several major workflows. And I have to warn you, these workflows are actually incredibly complex. So I'm going to walk through one or maybe two of them in detail. I'm going to explain everything, but these workflows are really complex. So if you want to learn TTK, there's a really steep learning curve. So you have to probably spend quite a few days going through these workflows yourself until you understand everything. But let's just try to work slowly through these workflows. So what I'm going to do is I'll drag my oops, this is not good. So just give me a second. So in the first flow, we'll create some toy function. We'll have 3 Gaussians. So the example you saw in 2D, and then we'll make this into a 3-dimensional, into a 2-dimensional surface in 3D. We apply programmable filter, and then we'll look for critical points, apply topological simplifications, and et cetera, et cetera. So let me actually give me a second. What I'm going to do is I want to, I want to show my slides on a different screen so I can actually follow the steps. And just give me a second. I have a sun here, so yeah, in the sun, it's impossible to see my screen. So here we go. I'm going to start a local, my local build of Paraview with TTK. So it's going to start Paraview 5.6. Here we go. And let me drag this zoom control. All right. And if I go to filters, you'll see that there are tons of TTK filters, right? So there are tons of TTK filters, and actually more here in the menus. And then if I go to sources, you'll see there are also TTK sources, right? So we know that this is a TTK-enabled version of Paraview. And it's actually enabled through a plugin, right? So if I go to tools and then manage plugin, you will see that one of the plugins is Topology Toolkit, so TTK, and it's loaded currently, right? So all is good. All right. So what we're going to do now is I'm going to construct this 2-dimensional function with 3 Gaussians. But before I construct the function, I need to define discretization. So I'm going to go to sources, and I'm going to sources, and I'm going to search for a plane source. So I'm going to create a plane at a resolution of 100 by 100 points. Right. So here's my 100 by 100 discretization. I can actually switch to wireframe. So you see 100 by 100 points, and it's in 2D. So by default, since I created a 2-dimensional object, now I'm looking at it in 2D. So next, I'm going to apply a Python calculator filter. So I'm going to introduce the first Gaussian, and I'm going to search for, so go to filters and search for Python. Oops, it's grayed out because I need to click on the plane. And then I'm going to search for a Python calculator filter. So Python calculator filter, and into this filter, I'm going to copy the expression from my notes. It's actually the same expression in the slide. And so the array name, the result is going to be called P1. This is my first Gaussian. And then the expression is going to be this one. So what's happening here is input 0 is the output of the plane source, right? So the plane source has has one output, and then that output is called plane 0. And that output has X and Y points. So these are X points, and these are Y points, right? So basically, I'm computing a Gaussian, which is centered at X equal to 0.28, and then Y equal to also 0.28. And then my domain goes from minus 1/2 to plus 1/2 in each dimension. And then the sigma, so the half width of the Gaussian is 0.02. So when applied, it will compute the Gaussian, and the Gaussian is called, so the output of this filter is called P1. So I can actually color by the Gaussian, and you can see there is a Gaussian right here in 2D. I'm going to introduce a couple of other Gaussians, so just bear with me. So I'm going to introduce another Python calculator filter. So search for Python calculator, and then I'm going to call it, the second Gaussian is going to be P2, and it's just a different expression. So here's my second Gaussian, and it's just offset relative to the first Gaussian. And then I'm going to have a smaller third Gaussian. So the third Gaussian, I'm also going to call the filter Python calculator. So Python, oops. Oh, I need to click on this guy and then bring up the Python calculator. So Python calculator, and then it's going to be called P3, and then the expression is just a smaller Gaussian. So smaller Gaussian, and here we have P3. I can visualize P3, right? So now I can actually add all 3 of them, and for that I don't need a Python calculator because I already have these 3 fields, P1, P2, and P3 defined. So I'm just going to call the usual calculator filter. So the result is going to be called P my Gaussian, and it's just the sum of the three Gaussians. So P1 plus P2 plus P3, right? So here's my function, two-dimensional function with the three Gaussians. And it's visualized into this. So if I try to spin it, you see that it's a two-dimensional view. So now what I'm going to do is I want to make it three-dimensional. So one option would be to apply the warp by scalar filter, but a warp by scalar filter actually, for some very detailed reasons, it doesn't really work very well in this case. So instead, I'm going to make it 3D using a programmable filter. And first, I'm going to switch from the Cartesian mesh to a tetrahedral mesh. So basically, I'm going to apply the tetrahedralized filter to the output of the calculated filter. So the output of that is going to be a bunch of triangles. And then these triangles I will make 3D. So these triangles will form a polygonal surface, right? So to the output of the calculated filter, I apply tetrahedralized filter. So tetrahedralized filter, basically converting this into a bunch of triangles. And then to tetrahedralized filter, I'm going to apply a programmable filter. So programmable filter. And I'm going through this step by step on purpose because, I mean, all TTK workflows are complex. And believe me, I've seen workflows with hundreds of steps in here. So this is a simple, relatively simple workflow with only a couple of dozen steps. So what I'm going to do now is into this programmable filter. I'm going to, so here, oops, sorry. Uh-oh, it crashed for me. Uh-oh, that's bad. All right, well, what I'm going to do is let me restart Paraview. So I'll restart Paraview. I'll just quickly go through the steps without annotating them. So, and then I'm going to save my state file as well, so that in case it crashes, I can recover very quickly. So I'm going to go to sources, search for a plane, and then bring up a plane at resolution 100 by 100. And then I click apply. To this plane, I'm going to apply the Python calculator filter. So it's called P1. And then the expression is going to be this guy. So apply. Then I'm going to apply another Python calculator filter. So this one is going to be called P2. And then the expression I'm going to copy from my notes. This is P2. And then finally, I'm going to have another expression, P3. So the expression is P3, and I have to make sure that I copy the right formula. So this is the right formula for P3. And just let me check very quickly. So I have P2, P1. Yeah, everything looks great. So I'm going to save the state file just in case it crashes. I'm going to save it into my data, into this state file. All right, so let me call it by P3, great. Then I'm going to introduce the calculator filter. So result is P, and it's just P1 plus P2 plus P3. I hit apply, call it by P2, by P. Let me tetrahedralize that. So convert it into triangles, apply, and then I'm going to save it, save the state just in case. All right, and then I'm going to apply the programmable filter. So I'm going to say programmable filter. And into the programmable filter, I'm going to paste the following expression. So I will explain what it means. So here we have the input to programmable filter is the same as output, right? So the input is a two-dimensional mesh with input, so there's a single input, input 0, and then it has a point data field on top of it. So the point data field is our Gaussian P, right? So here what I'm taking is I'm offsetting these into the third dimension. So the first line offsets this into the third dimension by the value of the function, right? By the value of the function P. And then I also, to this three-dimensional function, I also add the field called P, which is the same as the two-dimensional field P, right? So actually, sorry, it's going to be a two-dimensional function in 3D, right, on a polygonal mesh. So let me apply this, and then let me make it 3D, and then display that in 3D. So now I have my three-dimensional view, but it's still a two-dimensional surface. It's just visualized in 3D. So again, let me save it just in case it crashes. Okay. And then the next step is going to be, now we're going to be searching for critical points. So to the output of the programmable filter, I'm going to apply critical, I'll search for critical points. I'm going to apply TDK scale fill critical points filter. So I'm going to say apply. And these creates a bunch of points, but unfortunately we don't see them because they're infinitely small, so they're just points. And so next I need to convert these points into spheres. So I could do that with the standard glyph filter, but instead of the standard glyph filter, I'm going to search for a filter called TDK sphere from point. So here, search for filter. So I'm going to apply TDK sphere from point. And then I'll just accept the default value, and the spheres are very large, so obviously I need to decrease them in size. So let's try these radius. And so here are my critical points. And let's call these critical points by the critical type, right? So here I have my surface. Let's again save it, just in case it crashes. And the critical points. So the critical points, let me actually click on this guy, disable the color map here, and then click on this guy. So here the color map shows the, shows the critical points. So right here, we have the critical type going from 0 to 3. So actually there are integer values 0, 1, 2, and 3, right? So here, this is actually, I think this is maybe a bug. I'm not sure, maybe it's intentional in this particular filter. So, but the filter is actually confused a little bit about my data. So usually when you look at a two-dimensional function, there will be only 3 types of critical points. There will be minimum, maxima, and saddles, right? So, and so the critical type should run from 0, 1 to 2, right? So in this case, it runs from 0, 1, 2, and 3. And the reason for this is because I'm applying this filter to an object in 3-dimensional space. So it is a little bit confused about my function, but there are still only 3 types, not 4 types of critical points. So the critical points are the minima shown here in blue, then the saddles shown here in pale blue color, and then the maxima shown in red. So now you notice that there are also some spurious critical points caused by the boundary, right? So in fact, this guy, I mean, it's a saddle, right? I mean, it could be a saddle, but it's actually not, because the coordinate derivatives, not all coordinate derivatives here disappear. So the same here, right? So these actually spurious critical points. I mean, they are critical points for this data set, but they're not really critical points in the sense of these two-dimensional Gaussian, multi-Gaussian functions. So we're going to be removing them in our analysis. All right. So next, I'm going to create a new view. So I'm going to click on a new view, new render view. So this gives me a new window on the right. And then I'm going to apply to the my data set. So to actually a programmable filter, I'm going to apply the persistence diagram. So I'm going to go to filters and then search for persistence diagram. Okay? And then I hit apply. So this creates a persistence diagram that you saw in my previous slides, right? So the horizontal, the diagonal, and then you have a bunch of persistence intervals. So now let me edit the axis. So in the properties of the persistence diagram, I'm going to say bring up the show the axis grid, and then the x coordinate I'm going to call birth, and then the y coordinate. Actually, no, I'm going to call it value, and then the y coordinate I'm going to call it persistence. So this is the size of each component. Right? So I'm going to say OK, and then let me just save it just in case. All right. So now, next I'm going to apply a threshold. So the idea here is that I want to separate all the lines here in this plot, for example, the diagonal line and the actual persistence intervals. So to the output of the persistence diagram, I'm going to apply a threshold filter. So here's my threshold filter. And for the type of threshold, I'm going to say pair, let me just double check, pair identifier. So here the idea is that only non-negative values correspond to real persistence intervals. And so -1 is the diagonal, right? So I'm going to, in threshold, I'm going to remove negative values, and then I'm going to only show the persistence intervals themselves, not the diagonal, right? And then to this, I'm going to apply the calculated filter. So the reason being is, let me just go to my slides. So in the output of let's see. In the output of the persistence diagram, there are a number of variables, and one of these variables is pair type. So pair type actually lets me distinguish spurious or boundary critical points from the internal critical points. So I'm interested only in the internal critical points. So I want to throw away the spurious critical points. And the spurious critical points correspond to pair type 0. So what I want to do is I want to only keep pair type -1 and +1. But in this older version of Paraview 5.6, I don't have an option to invert my threshold interval, right? So what I'm going to do is I'm going to apply a calculated filter. I'm going to create a new variable called pair type 2, and this variable is just the absolute value of pair type. And then I'm going to apply a threshold on pair type 2, only keeping positive values, right? So basically throw away the boundary or spurious critical points. So to the output of this threshold, I'm going to apply a calculated filter. And then I'm going to pick up so the variable is going to be pair type that I'm going to use for calculation. So I just see, let's see, point data, cell data. Let me see. Here it is. Yeah, I switched to cell data, and then here I have pair type. So the absolute value, and I'm going to call it pair type 2. Pair type 2. And then I'm going to say apply, save these just in case, save state. And then next, I'm going to apply a threshold to the output of calculator. So here's my, my threshold. And here I'm only going to show positive values of pair type 2. I'm going to say apply. And then I'm going to pass this. I'm going to pass this to the, let's say, color by solid color. And then I want to show, let's see, I'm going to apply the extract surface and then tube filter so I can actually see the persistence intervals better. So to the output of second threshold, I'm going to apply the extract surface filter. And I'm almost done with this workflow. So with this example, so extract surface. And then I'm going to say apply. And then I'm going to save these just in case. All right. And then to the output of this, I'm going to apply the tube filter. So, and what this will do, it will simply make my actual persistence intervals bigger, right? So here are my 3 persistent intervals here, and they correspond to the 3 Gaussians, right? So now what I can do is, oh, actually, let me apply to this threshold, yet another threshold on persistence. So to this second threshold, I'm going to apply a third threshold filter on persistence. And so for now, I'm going to just select the entire range from the minimum to the maximum, right? So here's my entire range, but optionally, I can modify these bounds, and then I can simply show only certain persistence intervals. So I can get rid of, for example, of the small persistent intervals and only show the major peak or the major 2 peaks, all right? So next, what I'm going to do is let me apply TDK sphere from point to the last filter. So from point. And these will show on the right, these will show my critical points. So let's make them smaller. And so here are my critical points. I can type them, I can call them critical type. So in this case, you see that actually, no, it actually still shows, yeah, it still gives me the 3-dimensional critical points, but in fact, these are 2-dimensional critical points. So there are 3 types. There is a global maximum. There are, there are maxima, right, in red. There is a global minimum in blue, and then there are the saddle points in beige color. All right, so now let's perform topological simplification. I'm going to save this state. And next, the steps are in my slide. I'm going to apply topological simplification. And notice, by the way, here that I can actually show the other smaller persistence intervals that are caused by these spurious points at the edges, right? So these ones, and I simply do not include them into the analysis. All right. So now let me show you how to perform topological simplification. So I'm going to programmable filter. I'm going to, so my three-dimensional surface, or actually, here's my programmable filter. I'm going to apply the clean to grid filter. So I'm going to apply clean to grid. All right, say apply. Okay. Oh, actually, I probably want to introduce a new view, right? So I want to split the view, do render view, and then here I want to hide clean to green, and then here I'm going to show clean to grid. Right? So here's my three-dimensional view that looks identical to the original function, right? So far it looks identical. And now let's apply topological simplification. So this filter has two inputs. So simplification, topological simplification, two inputs. The first input domain is going to be so let me just double check to make sure that I don't make any errors. The domain is going to be the output of clean to grid, the last filter. And then the constraint is going to be the third threshold where I modify the persistence intervals, right? The persistence range. So I'm going to say, so make sure domain, we have clean to grid. And then for constraints, we have the third threshold where we're going to be modifying the persistence interval. All right. So I'm going to apply it. And then again, I need to make this three-dimensional. So to this topological simplification, I need to apply, let me just save this just in case. I need to apply the programmable filter, exactly the same programmable filter as before. So I'm going to go to actually apply, save this guy. And then I'm going to apply the programmable filter to make it three-dimensional as well, to make the function three-dimensional. So programmable filter. And then into the programmable filter, I'm going to paste exactly the same expression as before. So make our two-dimensional function three-dimensional, right? And then what we're looking here now is the output of the programmable filter. So now let me save again because I'm really paranoid that this whole thing will crash. And now I can color by color this view by the value of my function, my Gaussian, okay? So now let me connect the two views. So I'm going to say link camera, click on this guy, and now the two views are linked. So you can say, well, it's exactly the same. Yes, of course, because we have not modified, well, it's almost exactly the same. We have not really modified much the persistence intervals. So let's go to the last threshold filter and actually modify the persistence interval. So let's change that to a high value. And now you see that I actually performed topological simplification. So one of my peaks is gone. So you can see it on the left, but you cannot see it on the right, right? So I reduce, so basically I modify the range of persistent intervals that I'm going to keep. So I'll only keep persistent intervals with a persistent value in between this number and this number, right? So if I increase this guy, I can actually remove the second peak. I can remove the second peak and so on, right? So this is called topological simplification, and it works well for one-dimensional, two-dimensional, and three-dimensional data in TDK. So any questions so far? We have only 15 minutes left, so I don't think I'm going to walk you through live examples, but I'm going to show you many workflows. I'll preload them. I already have them saved as state files. So I'm going to just load them into Paraview. So if there are no questions, let's continue. Let me go to my slides. And then here, let's talk about the TDK more small complex filter. So this is one of the more complex filters in TDK that lets you output a bunch of things. So let's just start with a two-dimensional function in our previous example. And for this function, I don't need to construct it from scratch. I'm just going to load it from a state file. So I have a file called multi-Gaussian only Paraview state machine. Let me kill this Paraview. And in my terminal, let me go. So in my terminal, I'll go to my data. And then here, I'm going to start Paraview with the following state file. So it's multi-Gaussian and then multi-Gaussian only. So I'm just going to load the function only, right? So starting from the function, I'm going to, so I'll just give it a second. Here's my function. I'm going to apply the filter called TDK more small complex to the function, well, to the programmable filter, so the function in 3D. So I'm going to search for Morse small TDK more small complex, and then I just apply it. All right. So in the output of this function, you see there are a bunch of things that are added. There are critical points. There are one separate traces. There are two separate traces, and there is segmentation. So let's just visualize the critical points first. So actually, yeah, let's show segmentation as well so that we see the two-dimensional surface. So the critical points, of course, are not visible because they're very small, I mean, infinitely small. So we need to pass them again through this filter. So TDK sphere from point. I apply the filter, and of course, I need to reduce the size of the points. And here are my points. Let's color them by the cell dimension, which gives me the critical type. And actually, this time, this filter gives me the right, so it's not confused about three-dimensionality. The function is still two-dimensional, and it gives me three values, so 0, 1, and 2. So for the minima, saddle points, and maxima, right? So everything looks correct. So now let's take a look at the separate traces. So let's highlight one separate trace. So we're going to apply extract surface and then a tube filter to it. So I'm going to click on one separate trace, and then I'm going to just make them thicker. So I'm going to do extract surface, and then apply, and then so this converts extract surface basically converts a line into polygons, and to polygons I can apply the tube filter. So that will make these separate traces or the lines separating monotone regions thicker, right? So I can make it whatever I want. So any thickness for these tubes. And then let's click on segmentation, and then we'll color segmentation by either ascending manifold or descending manifold. So let's just try both. Let's go and color by ascending manifold. And here, as you can see, this shows the mountains. And if you color by the descending manifold, this shows the basins, right? All right. So this filter is really useful to give more small complex because it outputs, all these things in a single filter, and you can apply it to three-dimensional data set as well. So here is an example with noisy terrain, and this is the classical example from TDK tutorial. So this is actually their cover visualization. So you might have seen this in the announcements of this webinar, but basically if you go to any TDK tutorial, this is the first image they're gonna show you. And this is an example of a noisy terrain. So let me just go to this, well, let me just load this state file. So I'll go into TDK data directory, and then I'll load Morse persistence state file. So let me go there. TDK data. Oh, TDK data. Sorry. TDK. Oops. TDK data, and then I'm going to load from states Morse persistence state file. So ppp -- state is equal to states, and then Morse persistence. All right. So let's just give it a few seconds, and it will construct this cover visualization. So what is shown here is not just the function here on the left. So you also see the persistence diagram, and you see the persistence curve. So the persistence curve is basically the distribution of these intervals. So on the vertical axis, I have the number of persistence pairs, and then on the horizontal axis, I actually have the persistence interval itself. So you see there are a few large persistence intervals, and then as you decrease the threshold, the number increases, right? So you can actually mouse over these persistence curves, and it gives you, the value, the X and Y components, and that tells you that okay, above certain threshold, below certain threshold, I have a noise, right? So for example, here you have a plateau, and this plateau separates, meaningful peaks that are interesting to us from all the noise, right? So all the critical points left from this plateau represent noise. So there are hundreds and hundreds of noise intervals, intervals from noise, and then there are only 27 or so intervals from the meaningful data, right? So here you can actually play with one of these thresholds. So they call it persistent threshold, but it's just the name. So it's the usual threshold filter. They just renamed it right here in the pipeline browser to persistent threshold. And so here you can modify the persistence, so the minimum persistence, and you will see that what will happen is some persistent intervals disappear, and then you have more, you have more regions or fewer regions, more critical points, fewer critical points, and the same for the separate traces between these monotone regions. So if you want to show simplification for the two-dimensional function itself, for this two-dimensional surface, it's really easy to do that. So you basically need to apply the programmable filter, like in my previous example, to the output of the TTK topological simplification, and then making sure that you pass the blend variable. So in this case, in this specific example, the blend variable is actually the value of my function. And then you simply play with the persistence threshold, and then you will get simplification. So it'll be raising smaller peaks, and in this case, already started raising big peaks as well. Right? All right, so let's continue. Here's an example. I'm not going to run it, but in this example, what they do, so it's actually taken from Charles Guineux's tutorial from the IEEE conference from last month. And this is a cool example because it shows data segmentation, so three-dimensional function segmentation in TTK. Using a different approach. So here, what he does is he applies topological. So he basically looks for, he applies the persistence diagram, and then applies a threshold on persistence. So that lets him control the noise and exclude the noise from the three-dimensional data. And then he applies topological simplification. So this is actually, you simplify the function itself using this threshold. And then he applies the TTK merge contour tree FTM filter. So FTM stands for Fibonacci task-based merge tree. So basically the idea here is to identify the regions that are adjacent to the leaves, right? So the leaves correspond to the maxima in your three-dimensional function. So this maxima corresponds, so this is a three-dimensional scan of a human foot, and the maxima corresponds, so 5 maxima correspond to the 5 bones in the foot, so for 5 toes. And then to identify the regions that are adjacent to these 5 maxima, he applies to the topological simplification to remove the noise. Then to the topological simplification filter output, he applies this merge and contour tree FTM filter, and that produces a merge tree. And then one of the variables in the output of the merge tree is going to be called a variable region type. And then region type equal to 1 corresponds to the regions adjacent to the maxima, or to the leaves, right? So this way, he can actually perform three-dimensional segmentation. And if you go through all these steps, you will actually see how it's done. And it's pretty cool. But again, this is a more complex, even more complex workflow than the one I did before. So, and unfortunately, I don't have a lot of time, and I'm just going to leave it as a slide. So here we perform 3D segmentation, and here's an example of a same algorithm applied to a simpler function. So here I have an analytical function. So it's a three-dimensional function given by this formula defined inside a unit cube. So x1, x2, x3 go from 0 to 1. So it's a unit cube. And the idea is that it's a function with lots of local minima and maxima, right? So here you have the persistence diagram. You have all these, components as we sweep in the three-dimensional value function from -infinity to infinity. Then you apply the persistence threshold, you apply simplification, and then you extract the regions adjacent to the tree leaves. So basically, the regions adjacent to the maxima. So when you don't have when you're not filtering persistence, then you get lots of local maxima, and these are the regions that are adjacent to the maxima. So you start filtering, so increase the minimum threshold for persistence, and you see that there are fewer and fewer regions until you get to a single minimum maximum in your three-dimensional scalar function simplification, and then they just don't get any regions adjacent to the leaves because there are no leaves. There's just a single maximum and a single minimum, right? All right, let me go to the very last section, image segmentation. And for that, actually going to show you an example from the TTK tutorial. So I'm going to go to my data and apply load image processing modified state file. And believe me, it's a simplification from the tutorial. So it's actually a much simpler version. Actually, let me go here. And it's a much simpler version of the same pipeline. I removed some filters. So let me load the state file called image processing modified. So the idea here is we're loading a PNG image, and then we're calculating the gradient of this PNG image, and then we're applying topological simplification to this two-dimensional gradient function. So let's just give it a few seconds. So here we go. We have the original image, PNG image, and then we calculate the gradient of this image. So you can see compute derivative is actually, we're computing the scalar gradient, and then we apply simplification. So if we plot the persistence diagram, you see there are lots of small minima, so a lot of noise close to the diagonal. And then we apply the topological simplification filter. And then we apply, after simplification, so removing all the small noise, we apply the TTK more small complex filter that I showed you before that produces critical points, separate traces, and segmentation of my two-dimensional function, right? And then so to the output of segmentation, I apply the TTK identify randomizer filter so that, well, yeah, actually, well, you'll see why I need to apply it. So if I, instead of highlighting the output of randomizer, I show the output of non-random output, you see that there is simply monotonic increase in these region IDs, or these descending manifold IDs from top to bottom. But if I want to highlight, the fact that I do image segmentation, I can simply randomize all these regions, and here's what we get. So this works very well. And in fact, you can change the threshold for removing the noise, so increase the persistence threshold. And here I have a plot in my slides where I modify the persistence threshold, so increase it from 5 to 10 to 15, as it makes sense. The number of descending or ascending, basically number of manifolds decreases, right? So I get fewer and fewer regions, and for very high values of persistence, I get only a few regions in the output segmented image. So this algorithm works very well. And here I apply it to another image. So in this case, I took the image from the Wikipedia page on image segmentation. So it's an Aurora image, really nice, colorful image. I apply the same algorithm, and then here's my segmented image. So it works very, very well, right? Basically, just follow all the steps in the previous example. And this example, as I said, I probably should supply it. I'm going to upload it to the same page where I posted the slides as well. So the visualization page, I'm going to upload these examples as well, so you can actually recreate them on your computer. And so final words on image segmentation. One is that in these two examples, I was taking the PNG images, input images, and then I was computing the gradient and using this gradient as a two-dimensional scalar function. Unfortunately, this will not work for all images. So I can show you many examples where it doesn't work. So very noisy images, of surfaces or porosity, et cetera. So, if you have a rock and you just cut this rock and then take an image of this rock and you try to apply the same algorithm, this algorithm will not work. So it turns out that the trick here is really finding the scalar function that will work well for image segmentation. And apparently this is an active research area. So I've done tons of Googling. And here's actually a more complex example from TTK tutorials showing image segmentation of an image from cell microscopy. So it's based on its classical image in topology based on the textbook example. And let me just load it. So I'm going to go to the TTK data directory. Oops. Go to TTK data directory, and then the file is going to be called tribute. So ppp-state. So you'll see that it's a very noisy image. And this is the last example I'm going to show. So we're almost done. And so here's it is loading. So I'll just give it a second. Oh, no, it's not loading because instead of loading the state file, I loaded the image itself. So I need to load the state file, sorry, which has the same name, so tribute. So now it should work. All right, it's loading. And here's the image. And let me actually show you the original image. So here in this panel, I'm going to hide everything, and then I'm going to show you the original image. So you see that the original image is really very noisy. Here's the original image. And then we perform topological segmentation. So we break this into individual, so it's a multi-cell organism. And when we break this into individual cells, and the trick here is really finding the right scalar function. So in this case, the scalar function they used was something different, not the gradient, but something different based on the original PNG image. And yeah, so this is the trick. When you do image segmentation, you need to find the right scalar function. And then this is your job as a researcher to find the right scalar function, and then this algorithm works beautifully. So to summarize, so the example that, so unfortunately I'm out of time. So this example, I'll just leave it in the slides. So running Paraview plus TTK by Singularity on CEDA. So this is the steps you can follow. So basically, let me just walk you through. So here you download a Docker image from Docker Hub. So it's a Docker image. And then you convert this Docker image into a Singularity image. So usually you want to, because converting from Docker image to Singularity image usually takes quite a lot of resources. You don't want to do this on login node. So here I start an interactive job with Salok asking for 2 cores. And then I convert a Docker image into a Singularity image. So the image saved into a file called, in my case, Topology Toolkit 562.cif. And then, so here I'm done. And then here on, so in a separate, I set a separate job. So an interactive job, in this case, asking for 30 minutes, 3,600 megabytes memory, so supplying my account. I load the Singularity module, and then I start the Singularity container that I just built, so the Singularity image. And then when it starts, it will start the PV server, so Paraview server right inside. So it's going to be a serial Paraview server, and then it will be waiting on a port 1111 on a given compute node where your job started. And then you start, as usual, in client server Paraview, you start a client server. So basically Paraview, client server, a Paraview client on your computer. And then you connect this client to, so you organize port forwarding from your local port to a remote port on the compute node. And then you point your Paraview to the local port 1111, and then basically you go to file open. It will open a remote file on CEDA. You go to file load state. It will open a local state file, but this local state file can point to a remote file on CEDA, and then you can do your analysis. So here you don't actually have to install anything. You just download a Docker image, convert it to Singularity image, run the Singularity image, that starts your Paraview server, and then you connect it from the client, and it works really, really well. So just to summarize, because we are out of time, in my opinion, TK is really powerful tool. It's really fantastic, but there is a very steep learning curve. So it took me probably 2 or 3 weeks of quite intensive part-time work to become comfortable in all these examples. But once you spend this time and once you learn all the workflows, it actually all makes sense. But the workflows are very complex. So as you saw, I probably spent 15 or 20 minutes in this webinar just constructing one of the workflows. And so hopefully this gives you an idea of what you can do with TTK. And yeah, now it's time for questions. So I'll be happy to stay along and answer any questions. So there's a question from
actually, Alex, you have a question in the chat?
Yes, in the chat, yes. So there's a question from Yohai. Why use the gradient of the image rather than the pixel value? I cannot answer that simply because the pixel value will just, the answer is the pixel value will not work as well for image segmentation. So why, I don't know. So image segmentation is, as I said, is an active research area, and I cannot answer why. I'm just not a specialist in this field, so I don't know why. Mathematically, the gradient works better than the image, than the pixel value, one of the filters, red, green, or blue, for image segmentation. I don't know, but it's just the way it is. So yeah. Any other questions?
Can you hear me?
Yes, I can hear you. Yes, yeah, please go ahead.
I have a question. So the process that you showed in TTK and Paraview, it seems that it's very time consuming. So
yes.
We have a lot of data.
Yes.
Is there a way we automate this process?
Yes, of course. You automate this process via a Python script or via state file. So what I showed you, all the examples, most of the examples I showed you, I was not building them by hand, right? So I just was loading the example using Paraview state file, right? So you can save your workflow, your entire pipeline in Paraview as a state file, and you can just load this Paraview state file and just load the entire pipeline. And then you can modify, you can modify certain components, for example, the import to different input image here. So let's just wait a few seconds for this to load. And then you modify, one of these things. For example, the input image right now is this guy, is tribu.png, and I can modify it, right, to different input image by these dialogues. Or even better, you can write all of these, it's really equivalent, as a script, as a Python script, this entire workflow. You can just save it as a Python script. So go to File, Save State. But now instead of the PVSM file, you save it as a Python file. So this will give you Python script that corresponds to everything that you do here. and then you just load the state, you load this Paraview Python script from, from the GUI or without using the GUI. So, and then you modify in the script anything you want. So you can modify threshold, you can modify, the algorithm for calculating the scalar function, you can modify the input image name, etc., right? So yes, of course, every time you don't go through all these steps. I went through the steps so that I can actually show you the meaning of each step and why it's important. But of course, if for routine work, you don't go through all these steps manually, just blow the workflow.
And then if you have multiple mountains, then you
Yes.
can identify them easily. So
yes.
What I had in mind was that like you have your phone camera and it can detect the faces of different people. So if you have an image and we want to use the camera, like you're monitoring something
yes.
on the flight, you can do that.
Yes, you can do that. So yeah, this is alternative. So topological analysis for image segmentation is alternative to machine learning, right? So you can perform similar tasks to machine learning just using very different algorithms. But yes, you can identify. So the question is how there are two main questions. The first one is how to construct a scalar function that you're going to put into this pipeline, right, as the input of this entire pipeline. So how to compute the scalar function. So that's one unknown. And I don't have an answer. I mean, I have several examples, but the answer is you really have to experiment. And then the other thing is, how do you identify faces, right? So faces are going to probably be components in your, in this persistence diagram, in this analysis, components with some properties, like a certain, for example, certain value of the certain persistence value. Sorry, right? So you can actually filter those out, and then you can identify people's faces that way. But of course, it's different from machine learning. So I mean, this is an entirely different algorithm, and the purpose is different.